This is what the inside of a battery actually looks like. There's nothing futuristic about it at first glance. Just about 2 meters of thin metal foil coated with a dark chemical paste, tightly wound into a compact cylinder that weighs only around 45 grams. And yet, this simple structure forms some of the most advanced energy sources we have today. These batteries power laptops, electric vehicles, and even satellites circling Earth. They are, quite literally, the backbone of modern civilization. Still, a question keeps coming up: if lithium batteries are so important, why do they feel largely unchanged after all these years? Have we reached the limits of this technology, or are we standing on the edge of something entirely new? Let's explore how we got here. Back in the 1980s, the world saw its first commercially available mobile phone. It needed roughly 10 hours of charging to support just 30 minutes of talk time. By today's standards, that sounds almost absurd. Yet at the time, it was a glimpse into the future. It also made one thing clear: the company that could create a better battery would unlock a massive technological leap. A major step forward came later in that decade with the rise of lithium-ion technology. British scientist Stanley Whittingham was among the pioneers, experimenting with metallic lithium as the anode and titanium disulfide as the cathode. His early design could store far more energy than any battery before it. However, it came with a serious flaw. Metallic lithium is highly reactive, which caused the batteries to overheat and, in extreme cases, catch fire or explode. Building on this work, John Goodenough made a crucial discovery: lithium cobalt oxide could function as a far more effective cathode, dramatically boosting energy capacity. Then, a few years later, Akira Yoshino solved the remaining safety problem by replacing metallic lithium with a carbon-based anode. This change made the batteries far more stable and suitable for everyday use. Together, these breakthroughs paved the way for Sony to launch the first commercial lithium-ion battery in the early 1990s. That moment changed everything. Lithium-ion cells became the foundation of portable electronics and remain at the core of today's electric vehicles and large-scale energy storage systems. So what is really happening inside a battery? In simple terms, it's a system that traps energy in chemical form and then releases it as electricity whenever it's needed. Every battery is built around 3 core elements: a negative electrode called the anode, a positive electrode known as the cathode, and an electrolyte that allows charged particles to move between them. When a device is running, ions travel through the electrolyte from the anode to the cathode. This movement generates an electrical current that powers everything from small gadgets to large machines. When the battery is being charged, the direction of this ion flow is reversed, restoring the stored energy for later use. One of the most important, but rarely noticed, components is the separator. This thin barrier keeps the 2 electrodes from touching each other, preventing a dangerous short circuit, while still letting ions pass through. Another key detail appears during the very first charge: a delicate protective layer forms on the anode. This layer stabilizes the internal chemistry and is the reason lithium-ion batteries can survive hundreds or even thousands of charging cycles. The end result is a power source that combines high performance with low weight and compact size, all while remaining reusable over many years. Today, lithium-ion batteries sit at the center of a global market valued at around $100 billion. They supply energy to smartphones, laptops, electric cars, and much more. Their success comes from their ability to pack a lot of energy into a small space, operate reliably over long periods, and be recharged again and again. However, manufacturing these batteries is expensive and depends heavily on extracting materials like lithium, cobalt, and nickel, resources tied to environmental damage and geopolitical tensions. Although lithium-ion batteries are considered safe in everyday use, they are not completely risk-free. Physical impact, excessive heat, or production defects can trigger a chain reaction known as thermal runaway. In this scenario, the battery begins heating itself uncontrollably, releases flammable gases, and in rare cases can catch fire or explode. Because of these limitations, researchers and manufacturers worldwide are working to push battery technology beyond its current boundaries. One of the most promising solutions on the horizon is the solid-state battery, a design that replaces the liquid electrolyte with a solid material. Because solid-state batteries do not rely on liquid electrolytes like conventional cells, the primary risk of catching fire is largely removed. This alone makes them far safer by design. Beyond safety, they also promise major performance gains, higher energy capacity, a much longer operating life, and charging speeds that could shrink from hours to just minutes. The challenge, however, lies in manufacturing. Producing solid-state batteries remains extremely expensive, and researchers are still trying to identify the perfect combination of materials that allows ions to move through a solid electrolyte as smoothly and efficiently as they do in a liquid. Solving this problem is one of the toughest hurdles in modern energy research. But if it can be overcome, the impact could be transformative, triggering a true shift in how we store and use energy. This is why some of the world's biggest technology and automotive companies, including Toyota and Tesla, are investing heavily in solid-state development. At the same time, specialized startups such as QuantumScape and Solid Power are racing to bring this technology out of the lab and into real-world products. This channel is sponsored by Buddy, your AI mentor and digital companion. Simply visit Buddy FM to try it for free. Another promising direction in battery innovation is sodium-based technology. Unlike lithium, sodium is incredibly abundant. It can be found in seawater and widely throughout the Earth's crust, making it far cheaper and easier to obtain. The main drawback of sodium-based batteries is their lower energy density. To deliver the same amount of power, they need to be physically larger and significantly heavier than lithium-ion cells. However, this limitation becomes far less important in applications where size and weight are not critical factors. This is exactly why sodium batteries show strong promise in large-scale energy storage, such as solar power plants and wind farms. In these environments, cost efficiency and storage capacity matter far more than compact design. As a result, sodium-based systems are already being tested as a future solution for stabilizing renewable energy grids. Alongside this development, another battery technology is steadily gaining real-world traction: lithium iron phosphate batteries, commonly known as LFP cells. While they cannot store quite as much energy as traditional lithium-ion batteries, they offer several major advantages. They are cheaper to produce, chemically more stable, and can operate reliably for a much longer time. LFP batteries are also considerably safer, with a much lower risk of overheating or catching fire. Because of these benefits, Tesla has begun using them in certain vehicle models, while major Chinese manufacturers such as BYD and CATL are now producing them at massive scale. Thanks to this rapid adoption, LFP technology is becoming one of the key foundations of today's global battery industry. Another material generating enormous excitement is graphene. If scientists can fully unlock its capabilities, it could lead to batteries that recharge in minutes, survive thousands of charge cycles, and weigh far less than anything available today. At the moment, graphene-based batteries remain largely in the experimental stage, but their long-term potential is extraordinary. Lithium-ion technology reshaped the world and launched the digital age as we know it. And this is only the beginning. The rise of solid-state, sodium-based, and graphene batteries has the potential to completely change the rules within just a few years. In the near future, charging a phone might become a once-a-week task, electric cars could be ready to drive in just 3 minutes, and entire cities may be powered by energy stored inside massive battery systems. We may already be standing at the edge of the greatest energy transformation since electricity itself was first harnessed. If you enjoyed this video and want to explore more breakthroughs shaping the future, don't forget to like, subscribe, and turn on notifications so you never miss what's coming next. Thanks for watching, and I'll see you soon in the next episode.